Welcome back, ladies and gentlemen. Today we're going to conclude our instruction on standard deviation. Specifically today, we're going to learn about what a normal distribution is and what the 68, 95, 99.7 rule is, also known as the empirical rule. The first thing I want to talk to you a bit about is something called a normal curve, which is basically what a histogram would look like if you had a whole bunch of stuff in the data set, like thousands of items inside the data set. And if you made the bin width of a histogram very, very narrow. A normal curve specifically is when you have this clustering of a lot of different data points near the center of the curve or near the mean of the data set. You may have also heard of this as the bell curve, but we're going to refer to it as a normal curve. Now there's quite a few things that happen that fit a normal curve. So if you have a large enough population, you can basically think of anything with a large population, let's say people, and the stats from those people will fit what's known as the bell curve or normal curve. So if we surveyed everyone's weight or height or how much volume they take up or what their blood pressure is, the data that we got from each person, if we put it all in one place and kind of made a histogram out of it, we would basically make a normal curve. An example of exam scores is another one. You can do that with a pretty low number of people inside of a class, about an N of 50 usually works, and you'll get a nice bell curve. And when a teacher says they're grading on a curve, that's what they mean. They're saying that I'm going to adjust the grade scale so that not a huge number of people are failing and not a huge number of people are getting A's, no matter what the actual score of the test is. You maybe notice down here, percentage-wise, normally this would be normally a score of 50% would be failing and most of the people are there, so the professor would be likely to scale the grading scale down to call that maybe a C or something like that. There's a few things that are true about a normal curve no matter what. Firstly, a normal curve or a normal distribution is unimodal. That means it has one mode, and you can see here there's one peak for one mode. That's also the mean and the median, so all three measures of center stack up right in the middle there. The normal curve is symmetric about its mean, so there's no kind of asymmetry to it. It's nice. It's the same curve on both sides of the curve. And the last thing is that no matter how wide or how high this normal curve is, if you know the mean and you know the standard deviation, you can know where to put this left to right, and you can know how tall and wide it is just by having those two numbers. And what's nice about a normal curve is no matter where they're located left or right or how complicated of a data set they represent, basically, if you know their mean and their standard deviation, you can draw out a quick sketch of it and label an awful lot of numbers about the data set just with those two numbers. The next thing we're going to do is we're going to start putting a few numbers to this curve. So the first thing I want you to understand is that all of the possible things that could happen, all the possible measured results are under this curve. So if we think about this in terms of like a probability, if I added up all the possible outcomes underneath here, or the probabilities of those occurring, I would get 100% perfectly. The most common things are in this region right here, where you can see that the frequency is very tall, and the least likely or rare items are happening out here on the edges where I have this label of uncommon. No matter what the normal curve looks like, we can actually throw some more labels than just this on there. Firstly, the center of the curve will always be the mean, so I can put an X bar right there. And then our standard deviation is the average distance from the mean. So there will be an equal spacing of standard deviations to the left and to the right of the mean. So let's say my mean was 50 and my standard deviation was 10. This would be 50, 60, 70, 80, 90, and this would be 40, 30, 20, 10, and so on. The point here is that we can cut this normal curve up into multiple sections of standard deviation. So we're going to put our mean right here and go off to the left and right one standard deviation in each direction. Where do you put it? Well, the first one goes where there is a change in concavity on the normal curve. Now, we've talked about concavity a little bit with parabolas, and you can see here we have a downward-facing parabola, and you can see where it changes from a downward-facing parabola to an upward-facing, so kind of a frowny face situation to a smiley face situation, even though there's only half of a smiley face. But that point where it changes from frowny face to smiley face is called a point of inflection, and that's where you put your first standard deviation. Now, every set of data is going to have a different mean and a different standard deviation. So if we take a look at what effect the mean has on a normal curve, its shape and location, we can do something like this. So if we have a normal curve and its mean is right here, we would center the curve about right there. But if we increase the mean and say shift it over to the right, the whole curve will follow and be centered around that mean. If it had a lower mean, or we decreased the mean of a data set, then just the opposite happens. It would shift left and right. So basically the effect of the mean is that it shifts the whole curve left and right. If we play around with the standard deviation, so say we have this normal curve and we increase the standard deviation, that means we would be increasing the spread of the data. Well, what would happen then? The tails of the normal curve would get spread out left to right, and the peak would get down, because remember, the area under the curve still has to add up to be 100%. So if it's spread out over a wider left to right range, then the peak also has to go down. So this would be with a large standard deviation, and if we had a small standard deviation, that would mean that the distance to the mean on average would be smaller, so it would kind of scrunch up towards the middle, create a higher peak, and the little tails off to the left and the right would be smaller. And at present, this doesn't seem like a huge revelation, nor does it seem very useful, but we can actually put some pretty specific numbers to this based on some higher level math than we're going to do in this course. But I just want to show you how you can use just this bit of information to label a normal curve from scratch. So let's say the runtime of a given cell phone is 300 minutes before its battery dies, with a standard deviation of 25 minutes. Label a normal curve to represent the situation, or to model the situation. Well, it said the average runtime is 300, so we're going to throw that right down there in the middle. And the standard deviation of 25 minutes, that means that each of these tick marks, so I'm going to go find that point of inflection, drop it down to my x-axis right here, and I'm going to count up by 25s from 300, and I'm going to count backwards from 300 by increments of 25 as well. So every increment is going to be 25, my standard deviation. And if I could just continue that across my x-axis, I have that thing labeled and done. And once I have a normal curve labeled with what I know, I can start to use it to ask a few more difficult questions, like how likely is it for a cell phone to last more than 300 minutes? So that would mean all these cell phones over here. Now, since a normal curve is nice and symmetric, you'd probably say 50%, and you'd be absolutely right. So according to this graph, 50% of the cell phones are going to last longer than that. But then I can change the question, and I can ask more specific questions about a standard deviation away from the mean. So how many cell phones would last more than 325? So you can see that's no longer halfway. How about 400? That's way over here. How likely is it that these things will happen? Well, there's a rule to help us figure out what the probability of each of those segments is. And here it is. This is called the empirical rule, or the 68, 95, 99.7 rule, which is a mouthful, so I like saying the empirical rule. If there's one thing you need to take away from this video, it's basically everything on this screen right here. If you haven't already, start making a sketch of it, and if you have the note packet printed out, it's already done for you, but you need to have a picture of this labeled correctly. So pause the video right here and sketch it, or just know that you have it available to you in the notes packet. And what the empirical rule does is it breaks up a normal curve into certain zones, and it associates those zones with a number of probabilities. It says that 68% of the outcomes are going to occur within one standard deviation of the mean. So whatever our standard deviation is, you step over one standard deviation to the right and one standard deviation to the left, and almost 70% of the data is going to fall in that range. If we step out one more standard deviation, that covers 95% of the outcomes. And if we step out 3 standard deviations on each side of the mean, that's going to cover 99.7% of the outcomes. Now there's a little tail left over here for 0.15% on each side, and you can see the percents of just the single regions have been broken out for you as well. So half of 68 is 34. Half of the remainder of 95 is, this green segment only is 13.5%. This blue segment only is 2.35%, and this blank region right here, trailing all the way out to the right, the rest of the graph all the way to the right forever, is worth 0.15% on a normal curve. And if we apply some numbers to this, let's say male height in feet of the world's population, the average height being 5.5 feet with a standard deviation of 1/2 foot. We put our mean right in the middle, and we step by 1/2 feet each direction. We can say with certainty, having surveyed just a small population, that we can say 68% of the population is going to fall between 5 feet and 6 feet. If we step out one more, that means that 95% of males are between 4.5 feet and 6.5 feet. And if we were to step out one more, that would be 99.7% of males are between 4 and 7 feet. So the next slide, here's an example of what your problems are going to look like. It says the normal distribution below has a standard deviation of 10. approximately what area is contained between 70 and 90? Well, that's not around the center. You see that those are the two standard deviations off to the right. So this one has a mean of 70 and a standard deviation of 10. And you can see that it's only going to cover, like if we were to go left to right the whole way, that would be 95%, but we're only going to cover half of that. So we're going to chop the 95 in half to get 47.5%. Here's a second one. For the normal distribution below, approximately what area is contained between -2 and +1. So if we look at this, it's a little asymmetric again, and we still have that 47.5% that we figured out on the right half of the graph. Well, it's the same on the left half. And then you notice that we're stepping out one standard deviation to the right here, so that would be between these two standard deviations. So this chunk and this chunk, that would be 68. And if I chop 68 in half, I get 34. So I got that area plus that area, and I add those two together simply, 81.5%. Here's an even more stripped down version talking about the SAT. The average SAT score is 1,000 points with a standard deviation of 200 points. Label the normal distribution curve, and then we'll answer some questions about it. So if I know the average is 1,000, I'm going to put that right in the middle, and then I'm going to step to the right and to the left of it by a standard deviation of 200. So I label my axis just like that, and now it's set up in a way that I can answer questions about it. So I can say what percentage of students are expected to score above 1,400. So that's going to be right here. That is 2 standard deviations to the right of the mean. So I'm going to go ahead and just jot some more stuff in here. Just put those percents from that same empirical rule slide. I'm just going to label all the percents here, and then above 1,400, so that would be 2.35 plus 0.15 for a total of 2.5%. And what percentage of students are expected between 800 and 1,400? See the answer right there. Let's figure out how they did that. So 800 to 1,400 would be these three regions right here. So we got 34 plus 34 plus 13.5% to get 81.5%. Your homework is much of the same. There's a Stats 6b worksheet to complete, and on Schoology, you're going to report your solutions to number 3 and number 4. I'll see you next time.